Hi everyone, I am back and I am going to walk us through how to find the cube root of negative 4 root 2 plus 4 root 2 times a. That is, we're going to find a cube root of a complex number. And for us to start this example, we want to draw that complex number in the complex plane. It has a negative real part and a positive imaginary part, putting us into the second quadrant. I'm just going to put these values 4 root 2I and negative 4 root 2 at about the same distance on the axes. And they're the same number except for one's positive, one's negative, so the same distance from the origin. And then that allows us to plot our complex number here as negative 4 root 2 plus 4 root 2I. I'm not really concerned with the approximate values for these at all. I just care that it's the same value. And that allows us to see that this should give us a standard angle of 3 pi over 4. Yeah? The radius here for this complex number we can get using a Pythagorean theorem on this right triangle. So r squared equals 4 root 2 squared plus 4 root 2 squared. So r is going to equal the square root of 16 times 2 plus 16 times 2. That's 32 plus 32 is 64, giving us a radius of 8. So this is just a nice problem in that the values given for the complex number allow us to quickly tell what our angle is. Remember, if that's not apparent, you would need that the tangent of theta equals b over a, where the complex number z is equal to a plus bi. Yeah? And when you isolate the theta, you might need to add pi to make sure that you're in the right quadrant. Let me actually continue on that for just a second. So if we, for this problem, tangent of theta is equal to the b is 4 root 2, the a is negative 4 root 2, and those reduce to negative 1. That negative 1 is actually the slope of the line that we drew from our complex point to the origin. And if we tried to move the tangent to the other side, tangent inverse of negative 1 would output negative pi over 4 due to the range of tangent inverse. So we would want to add pi to that. To rotate us around to the second quadrant is the idea. So yeah, that I don't want to get into the details of that, but if we're in quadrant 2, we need to add pi to the tangent inverse if we're going about it that way. Okay, with this we have our radius of 8, we have our theta of 3 pi over 4. We can take our complex number z, which in standard form is negative 4 root 2 plus 4 root 2 times I, and rewrite it in its polar form as 8 times e to the 3 pi over 4 times I. And then if we want to take a cube root of this value, that's z to the 1/3 power in exponent form. So this is going to be the polar form, 8 times e to the 3 pi over 4 times I, all to the 1/3 power. And we can then distribute that 1/3 power to the 8 and the e to the 3 pi over 4. And when you do that, you multiply those exponents together. So you get e to the 3 pi over 4i times 1/3. And this is all multiplication, so we can just reduce those 3's there. Now the first bit, 8 to the 1/3, that's a 2. That's a cube root of 8. Gives us a 2. And then we will have e to the pi over 4I. Now, formulaically, we get that r e to the theta times I is equal to r cosine of theta plus r sine of theta times I. And I'm going to draw that picture again. So we have a radius of 2 and an angle of pi over 4. So here's a radius of 2, an angle of pi over 4 is going to put us right about here. And so if we want this x and y value, or rather not x and y value, but this real and imaginary value for this location, then we can use some right triangle trig here, where this, I want to say this, the cosine of pi over 4 is the adjacent a over the hypotenuse of 2, or a equals 2 times the cosine of pi over 4. And that's where we're really getting this in the formula. The r cosine of theta is the real part. And we also have, let's move this out of the way. That sine of pi over 4 is b over 2, or b equals 2 times sine of pi over 4. Should probably have an I right here next to that too. And cosine of pi over 4 and sine of pi over 4 are both root 2 over 2. So we can simplify these down to just the square root of 2. And so a is our real part and b is our imaginary part, and we can rewrite this cube root as the square root of 2 plus the square root of 2i. Let's switch these to put in the same order that we like to write it. There we go. This is our cube root, and this is essentially what you're responsible for being able to do, is just find a cube root here. In the previous example, previous video, we did a square root. If you're interested, you can keep watching. I'm going to go into some fun little factoids here. I said that this has actually 3 different cube roots. This is the primary cube root, and there's 2 others. If we go back to the solving for this angle, we could actually rewrite that. Instead of just 3 pi over 4, we could say that theta equals 3 pi over 4 plus 2 pi k for all of the other solutions. And that would give us that our original z is going to be 8 times e to the 3 pi over 4 plus 2 pi k times I. So all of these are our different thetas. Then z to the 1/3 is going to be 2 times, get a little bit more space here, 2 times e to the 1/3 times 3 pi over 4 plus 2 pi k. I don't want to belabor this, I'm skipping some steps. This is more just out of interest. If you're interested, you don't have to be able to do this. I would distribute the 1/3 across and get 2 times e to the pi over 4 plus 2 pi over 3k times I. And we can choose k as 0, 1, and 2 and get unique answers here. So we will have the cube root, the first cube root. Let's give this another letter. Let's call this C for cube root. So the first cube root is when k is 0, is 2e to the pi over 4 times I. That's the one that we already found. C1, our next cube root, is 2e to the, if k is 1 and we add these together, pi over 4 plus 2 pi over 3, if we get a common denominator, then we'd have 3 pi plus 8 pi all over 12. This is 11 pi over 12. So we'd have 11 pi over 12 times I, and then our third solution, when k equals 2, would be 2e to the, if I add another 8 pi over 12, let me write this like this. Like that 2 pi over 3 is an 8 pi over 12. So if we add another 8 pi over 12 to the 11 pi over 12, we get 19 pi over 12 times, times I. Sorry, this isn't going to let me scroll anymore. So we get these 3 different solutions, and you could convert all of these back into standard form. The fun bit of this that I really like is you can actually see this all pictorially. I don't have space on that. Okay, add a page. It does not. Here we go. Yay. Our original picture. It's my favorite bit. Original picture, real axis, imaginary axis. It gave us this point out here, and this has a radius of 8. Yeah? And we take that radius of 8 and we cube root it because we're cube rooting. And we can bring it down to a 2, okay? And then what we do is we take this angle and we divide it by 3. This angle was 3 pi over 4. If we divide it by 3, you're going to get this. Sorry, let me rewrite that. 3 pi over 4 in a smarter place. 3 pi over 4. And we draw 1/3 of that here. Oh, and we bring it down so it has a length of just 2, yeah? And then what we do is we cut the whole circle into thirds. So if I took the full 360 degrees and cut that into thirds, these so it creates this symmetrical shape around the origin of where these are. So those 3 different values. This is 2e to the pi over 4i, and this is 2e to the 11 pi over 12i, and 2e to the 19 pi over 12i. But this is just a pictorial way of taking those cube roots and seeing where they are in the complex plane. And again, you aren't going to be asked to do that But if you stuck around, then that's just a fun extension. If you take a complex analysis course one day, then you do this kind of stuff. It's pretty fun. Okay, I'll leave it at that. Thanks, everyone, and I hope you have a great day and a great weekend. Take care.